Hello everybody, my name is Marc Tudurí, and today I'm going to talk from PIDs to PODs, the life cycle of an eBPF-Auto-instrumented application. This is going to be about the journey that we did to run eBPF to auto-instrument applications in the Kubernetes environment. A bit about me: I work as a software engineer at Grafana Labs, more specifically on the Beyla project is what I'm going to talk about today. I'm a Prometheus contributor, an OpenTelemetry member. I'm currently based in Berlin, and during my free time, I mostly play drums, but in the past, I also recorded a few albums, and sometimes I also brew beer at home and cooking as well. Yeah, so this is the overview for today. First of all, we're going to talk about the challenges of manual instrumentation and how, thanks to technologies like eBPF, we can do automatic instrumentation. First, we have to talk about what is eBPF. So we're going to do a brief introduction and what are the main challenges of this technology. And we're going to continue talking about how do we make Beyla the first citizen in Kubernetes. We're going to continue talking about the challenges of running Beyla in Kubernetes. We're gonna see a short demo. We're gonna talk about future considerations, and then we're gonna wrap up. All right. So what is this automatic instrumentation with eBPF? So let's assume that we have our application, a web service, for example. So we want to see how is our performance, how is our service behaving in our system, right? So typically we can use what is called red metrics, which is the request per second, the error rate, and the latency of our services. We can also use traces, which allows us to have more debug information when services are connected among others. And we can either use a collector to scrape all of this data, or we can push all the data directly to a backend storage. But the bad news is that we have to instrument. And in the case of compiled languages such as Rust or Go, we have to do manual instrumentation, which means that in each piece of code function, we have to use a specific framework or like functionalities to measure our code. And in the case of dynamic languages such as Python or Java, we can use OpenTelemetry instrumentation, which is some sort of libraries that we either with monkey patching or inserting agents in our Java environment, we are able to get metrics automatically. But what if my runtime is too old? So it can happen that I'm using a version of the language or a framework that is not compatible with specific instrumentation libraries, or simply so those libraries that are in too much overhead, they're in too much memory, or just I have working with a legacy application, or it's just a compiled binary and I don't know what's going on there, so I cannot instrument anything, or I just don't want to mess up my code. It's happened often that now I'm using this new fancy instrumentation library, and then at some point it's gone. And what if I just want instant visibility of what's going on my service? I don't want to plan work. I don't want to have to wait. I want it now. So what if I told you that we can do this automatically? Let me introduce Beyla. Is our approach to automatic instrumentation. Initially, it was born as a Go automatic instrumentation because, as I said, in OpenTelemetry ecosystem, there is like different auto instrumentation libraries for different languages. But nowadays, Beyla is able to instrument any service in any language. It requires no agents, no code, no configuration changes. It's just a simple process that is attached to your application and is doing the magic for you. It can either get metrics or traces, and those can be in Prometheus or OpenTelemetry format. And also good is that it has no vendor locking. So at any time you can delete the container or the process and you're good to go. So, but what is eBPF? We don't have a lot of time to explain this, but let's see a brief introduction as it's a complex topic. So eBPF stands for this thing, not anymore, which doesn't mean anything. Now it stands for endless bugs, painful fixes. If you think that joke was not funny, it's because ChatGPT wrote for me. But yeah, so we can see eBPF as a virtual machine built into a Linux kernel. It works like a kind of a event-driven programming, where you have hooks, and these hooks are programs that they can be attached to kernel function or user space programs. It's complex as it requires to know how the memory is laid out. It's very low level. So you need to know how the function call arguments are done and how the local variables and return values are stored in your stack. Let's see a simple example. We have this sysconnect kernel function, which tracks a new client TCP connection. So we have a probe written in this eBPF language, which is a subset of C, and we attach it to the sysconnect kernel function. At the same time, we have a monitor program. You can write in any language. In our case, it's Go. And what we're going to do is we're going to compile this probe, and we're going to have a binary. The monitor program loads the probe from the compiled binary, and an app in the user space executes the sysconnect function, and this is going to trigger the probe. So the probe is going to do something. It can calculate something, and is going to start in what we call BPF maps, which is basically like some sort of ring buffer which stores data, and the monitor program is going to be able to read that data from the ring buffer. So in the monitor program, then you can do further calculations. So we want to keep like minimal business logic in the BPF probe because we have to write in C, and in a user space we can do more stuff because we also have access to network, and in the context of BPF is more limited. A bit of the pros and cons. Is fast, is just-in-time compiled, so the probes take not so much to run and compile. Is it safe, so you cannot be like do like a hacker man and like do infinite loops or access to positions of the memory that are forbidden. And it's also easy to clean up, as like once the monitor terminates, in this case the Go program, all the resources are automatically deallocated. So the cons is that it's hard to debug and write. I don't know you, but last time that I wrote anything in C was in the university, and that was like a long time ago. And it depends on the architecture. So if you are using ARM or 64 bytes, it's it's not compatible. And depending on the US eBPF functions, you need to run the program with elevated permissions. Okay. Now that we've seen what is eBPF, how do we make all of this work in the Kubernetes environment? So let's get the basic idea of Beyla running in a Kubernetes. In this case, we have Beyla running as a sidecar container. So it's attached to the application running in our pod. In this case, we have a request, which is get users, that goes to our application. So Beyla is going to execute its probes, and it's going to do some calculations. And in this case, we're going to measure the latency of this request. So we're going to generate a metric, in this case, HTTP request duration, and we are able to infer some data like path and the method, and finally the latency for that. This is good, but we need more than that because we are running in the Kubernetes environment, right? So our desired architecture deployment mode for Beyla is use daemon set. That's our default value in our Helm chart as well. This is better because it uses less resources, and we're going to have like a Beyla pod per node, and it's going to listen all the pods in that node. We require some changes in the container parameters. We have to set the privilege flag to true. This is because we need to mount the VPS file system. We're going to see later why we need that. And we also need the host PID set to true, which is going to allow the pod to have access to the host process ID of the node. So what Beyla directly sees at the host level, very basic information like the command name, the process ID, and the host name. But we need more than that because users, they want to, for example, in the example of the get user request before, they want to see in which pod, in which node, or in which namespace that request was executed. So how do we do this? So now let's talk about the journey from a PID to a pod. So we have to find out how the matching of processes with Kubernetes metadata works. The problem here is that we don't have a direct mapping between host PID and Kubernetes metadata. We don't have that magic implemented anywhere. So Beyla is gonna, first of all, of any instrumented process or pod, is gonna fetch from the /proc file system some metadata at OS level and also runtime metrics. The probe that is executed is going to be able to fetch application level and runtime metrics. And from the Kubernetes API, we're going to have access to pods metadata or the node metadata. There's a big challenge here. How do we match PID with pod? So we're playing here in a God mode. Because the same process with, depending on the point of view, we're going to have different PIDs. So for example, when the probe is executed, the PID at the kernel level is this specific number, but the one provided by the container runtime, when you set host PID to true, is different. If you are running Beyla as a sidecar container, the PID is going to be the one on the pod, and it's going to be just one. How do we match all of these together? First of all, Beyla is going to go to the /proc file system, and in here it's going to be able to get two elements. One is the local PID namespace at the host level, and the container ID. Luckily, the Kubernetes API, besides providing all the metadata from the pod, it also provides the container ID. With these two, we can relate PIDs and pods. But we have a missing component here because we still have to relate what is seen by the probes. Because the probes are helpful to get like all the information for application span, like we saw before, like the method and the path of the request, but the PID namespace is not straightforward. And this is what we need to figure out in order to glue all these pieces together. Yeah, so this is where all the puzzle begins. So in eBPF, there is a helper called getCurrentPID, and this allows us to get the PID of the running process. But this is, as we saw before, it depends on the context. So in a Kubernetes context, this information is not going to be the same as seen by Beyla. So we can use a different helper, which is called getCurrentTask, and it returns this nested struct with a lot of information that mostly I don't know what it is. But what is important here is that there's in this nested struct, there is we can access to the outmost namespace, and there is this object called PID namespace, and it has this level integer, which is tell us in which depth of the namespace hierarchy the process is running. So we grab that level. Next, we go to the thread PID struct, and it has this numbers array, and in this array there's all the PIDs of that process in different levels. In this case, we're just going to match the level that we got before in these numbers, and voila, we're going to have the PID namespace. This seems straightforward, but it took us some weeks to figure out. Just to recap, what's the journey of an application trace? So a service request comes in, and this triggers up the probe. And the probe, as we saw before, it gets a lot of host and request data. And then we have the process of matching the PIDs with pods, as we saw before. And we run the Kubernetes metadata decorator, which is basically adding Kubernetes metadata to the request. Finally, with that, we can generate either metrics or traces and export them in OpenTelemetry or Prometheus. All right, now it's time for a demo. This is how the config looks for the values YAML for the Helm chart. First of all, we have to enable the Kubernetes decoration. In this case, we are using Prometheus export to get all the metrics. And we have the discovery sections, which is basically how we tell Beyla what has to instrument. In this case, we instrument any deployment and any daemon set in the namespace default. For this example, we run in OpenTelemetry demo Helm chart, which is an e-commerce with deployed as a microservice architecture in different languages, as you can see on the bottom. And those services are calling each other with different protocols, either HTTP and gRPC. We track all of that. Okay, so now let's see the demo. Yeah, so we have here in K9s, we can see all the applications running. And yeah, so if we go to the daemon set section, we can effectively see that we are running Beyla as a daemon set, and it has 3 nodes, 3 pods, because we have 3 nodes. Yeah, and we can see here all the pods running for here in Beyla and also for the different demo services. And if you see here the logs, we can see a lot of things going on from the BPF debug as well. Right? And so Beyla is running, is doing instrumenting the services. So how does it look in Grafana? Yeah, so for this example, I just want to show you like that we have the Prometheus Explorer here, and in this case we are just querying the HTTP server request duration. Yeah, so a lot of metrics here, a lot of data. Yeah, so you can use this to build your own panel, but just for demonstration purposes, I'm going to show how does it look in application observability in Grafana Cloud. And in here we can see that we have all the instrumented services. So we can just, for example, drill down in this checkout service, which is a Go service. Yeah, so we can see here, as I said before, the duration, the error rate, and the request rate. Yeah, and yeah, we can also see like individual services, in this case, place order, and metrics for this operation. And we can also see here the downstream and upstream dependencies, which is easier to visualize in this section, which is Beyla automatically builds a graph of dependencies. It's going to be something similar as we've seen before in the diagram architecture. And in this case, we can see like how each individual service contributes to the latency of this service. So yeah, this is Beyla. It's a zero code instrumentation, and it provides like instant visibility for you without doing much. What's in the roadmap for the near future? First of all, we are working on reducing privileges. Currently, you need to run Beyla as a privileged container, as we've seen before. This is required because we need to mount the BPF file system, and that's needed because we have what is called the pin maps. But we found out that we can use BPF maps without pinning them. The pinning is just to like different processes be able to access to the shared maps. So we were working on not using these pin maps anymore, but you're still gonna need to run Beyla with some capabilities. At the same time, we are working on improving performance on Kubernetes informers. Currently, the Kubernetes informers have quadratic complexity because they are fetching all metadata from all the pods in the node, and that makes like super inefficient. We even brought down a cluster because we did DDoS Google Cloud, and yeah, so we are working on a centralized cache of objects. So it's going to be just a single pod, like fetching all the metadata, and the rest of pods they're going to access to that data. Okay, just to wrap up, we have seen how eBPF is a powerful tool. For observability, it's very useful. There are other projects that use for networking and security, but at the same time, it's hard to master, hard to debug, and you need to know like low-level stuff. We have seen how powerful is Beyla to do automatic instrumentation for you. We also have seen the challenges to make this work in the Kubernetes environment. And finally, we have seen what is in our roadmap to make Beyla more robust and performant. So that's it for today. Thanks a lot. And if you have any questions.